Hi, my name is Eduardo, and I'm going to talk a little bit about conformal layers, a nonlinear sequential neural network with associative layers. This work was developed by me, Leandro Fernandes, and Cristina Vasconcelos. First, a little bit about convolutional neural networks, or CNNs. They are well suited for signal processing like images and sounds and have applications in astronomy, biology, robotics, and security. Its main components are convolutional layers. Despite the name, they perform cross-correlation operations over the signal in order to extract the features needed for the task that the network was designed for. The dense or fully connected layers perform linear transformations using the weights and the input signal. Finally, the activation layers encodes the activation functions. These functions are typically nonlinear in order to extract the nonlinear interactions between the features. Because of this nonlinearity, they are not implemented using tensors like the other layers. Instead, they are based on element-wise functions applied to the tensors. And here is our problem. Since they are not representable as tensors, we can't use the associative property of these layers. In this context, associativity refers to the property of a binary operation on a set that satisfies this equality. Thus, we propose a new function based on linear operations, but without lose the ability to model nonlinear relations between the features. RES-Pro stands for reflection, scaling, and projection. Let's check how it works. Consider a one-dimensional space with 2 points, Z and X, that are alpha and delta units from the origin, respectively. Now consider that we are adding one more dimension to the space, orthogonal to the first one. In this new dimension, we have an hypersphere with center C and radius with alpha units. Now let's use this hypersphere as a mirror to reflect the initial points. We have one interesting property of reflections in hyperspheres here. Points on the infinity will be mapped to the center of the sphere, while points close to the edge of the sphere will be mapped to points also close to the edge of the sphere. It looks like a nonlinear behavior, right? But we'll get there. Now let's get our points Z prime and X prime as reflections of Z and X over the hypersphere. Now let's use the scaling part. By scaling the vectors that encode the points by a factor of 2 over alpha, we have now Z double prime and X double prime. Finally, by projecting the points back to the original space, we notice that the point Z, which was originally at minus alpha, is now at -1, while X, that was at delta, is now at Y. Basically, points in the range between 0 and alpha were mapped to the range between 0 and 1. We can generalize this aspect considering that the aggregation of these transformations define a function that maps X into Y subject to squared norm of X is between 0 and alpha, and the squared norm of Y is between 0 and 1. Great, but how can we include these extra dimensions and model these reflections in a linear way, but with this nonlinear behavior? We resort to the conformal model of geometry. By actually adding 2 dimensions to the space, a finite point in this model is defined like this, where we have a scaling factor, the Euclidean portion of the vector, a coordinate associated to the point at the origin, and a coordinate associated to a point at the infinity. Okay, but can we make it simple? Yes. On the supplementary material of the paper, we have the full algebraic manipulation that leads from the embedding on the conformal space to the tensor representation that we're going to explore now. Let's assume we have a point X lying on the D+1 dimension space. This point is represented by this vector that encodes the input data to our activation function. Notice that we have an extra dimension here. Our point Y that represents the output of the activation function looks like this. Notice that the Euclidean portion of this output point is the same as defined in X. The extra dimension, let's call it a homogeneous coordinate, is given like this. To get the value of y, all we need to do is divide each component by this value at the end of the process. We can rewrite these points like this, where Fm is almost an identity matrix, except by the last element, which is alpha divided by 2. Ft is a rank 3 tensor, almost full of zeros, except for the last slice, where we have almost a diagonal matrix with 1 divided by 2 alpha, except for the last element, which is 0. You're probably wondering, what does this function look like? This is an example. In this case, we assume alpha equals 3 and a dimensional input point, and a 2-dimensional input point. Well, 3-dimensional if you consider the extra dimension. The disk shape here is a consequence of the alpha definition. But how it fits in a neural network composition? Consider a layer of a neural network. Notice that this formulation is almost the same as the previous one, except with its tensor U. This tensor U encodes any linear operation applied to X before the activation function. It could be a convolution or an average Boolean, for example. This formulation can be intentionally rewritten like this. Now the composition of a neural network, considering the nested layers, can be written as a recursion, where the output of one layer is used as input for the next one. By expanding this recursion, we get this formulation, where Lm is defined by a productory of all the KFMs and U's from previous layers, and LT is defined as the summation. Looks complex, right? But it have its advantages. You should notice that Lm and LT does not depend on the X to perform these computations. In practical terms, it means that these values can be pre-calculated after the training and be used on the inference process. In summary, we've reduced our inference process, regardless of the depth of a network, to 2 tensor products and 1 tensor summation. Let's check the experiment and results. Our first experiment aims to check if our activation function is better than a simple linear activation function. The architectures are based on a simple convolutional layer with linear activation and fully connected layers, convolutional layer with ReLU as activation, and a convolutional layer implemented in associative way using ConformalLayers and RES Pro. We've evaluated 3 data sets: MNIST, Fashion MNIST, and Cypher10. The base RES Pro net provides higher accuracy when compared to base linear net, with improvement ranging from 1.36% to 2.76%, and lower accuracy when compared to base ReLU net, with a decrease from 1.95 to 7.61%. The relatively small drawback when compared to approaches implemented with ReLU are mostly due to absence of bias in our approach, which we are still working on, and the gap between the squared norm and the alpha parameter value. In our second experiment, we wanted to assess the quality of our approach with more robust architectures. Thus, we choose a LiNet5 architecture that can provide good results while still being a relatively simple network. We noticed that since the network is deeper, we're able to model more complex data when compared to the previous experiment. Additionally, we found smaller difference when compared to the previous experiment due to the same limitation. Our next experiment wanted to assess the inference time as the network gets deeper. As we can notice, we have constant inference time for conformal layers based networks, while having a monotonically crescent linear curve for conventional approaches. Notice that after around 9 layers, our approach is more profitable for implementations. And finally, we show the performance of our network as the batch size is increased. Conventional CNNs show some limitation around 18,000 images. while conformal layers were able to support 81,000 images. Under the inference time perspective, we noticed that our approach is faster. For batch sizes higher than 14,000, we had to use linear regression to estimate the values for conventional CNNs. This is due to the memory usage of this non-associative approach. Using the same amount of memory, we could run a batch 5.5 times larger. We've now presented conformal layers, and here are some conclusions. We have a new nonlinear and differentiable activation function. We have the first approach for sequential layers of CNNs where the linear and nonlinear layers are associative. We have depth-independent inference time with low memory footprint. And we have a relatively small drawback on accuracy, mostly due to absence of bias on conformal layers-based CNNs and the alpha parameter fit, which we are still working on. Thank you.